Hey everyone, we're going to get the talk started in the afternoon here. First, join me in welcoming Thalia from Simmons University, who will be speaking about performance boosting methods in semi-supervised NLP neural net environments. Please give me a warm welcome.
Hello, my name is Thalia. I'm so grateful to be here on this panel, and the last few hours have been full of camaraderie and shows me how much we can learn and teach each other in a few minutes. But since this field is older than a few minutes, and since we're already short on time, I thought I would take us briefly back to the late 90s. Exactly. So that was when the public necessity of the internet was really being brought on largely by the commercialization of the internet. If anyone remembers GoTo.com, which was acquired in 2003, that was the first search ad keyword service. And I like this quote from Dr. Avram Bloom. The web has hundreds of millions of unlabeled web pages that can be inexpensively gathered using a web crawler. Not because it's profound, but because it's true and sufficient. And because he said this in July of 1998. And I bring this up not only for the prescient commentary on web popularity, but as a framework to try and capture the trade-off that we have already made between what is and the knowledge that we have about what already is, and the nonlinear relationship that they have to each other. So this talk is based on a paper that I'm writing about research conducted this summer while working at MIT's Deep Neural Networks Coding and Engineering Lab. And the paper's goal is to utilize a set of statistical techniques to identify and group big text data. But the goal for this talk, if you'll just grant me the second premise, which is, in many machine learning settings, unlabeled examples dwarf the labeled ones. My goal for this talk will be to meditate together about some of the context for, the qualitative context for augmenting our learning behavior with machine algorithms. Let's see. Here, so with that in mind, my title is Performance Boosting Methods in Semi-Supervised Environments, and the method I'm addressing today is co-training. And co-training is the practical application of, more generally, any kind of method that requires two views of data. We have small labeled data, which is expensive to collect and moderate, and we have vast amounts of unlabeled data. It doesn't take long to write a web scraper, and that can produce massive data lakes. And the problem that we've been straddling is trying to use these two in tandem and use those trade-offs to our advantage. So again, it's a learning framework and nothing more. Co-training just means the two. So this, as you might have guessed, is a new development to an old problem. Before I came to speak, but after I'd already submitted the abstract for this paper, Google recently introduced, come on in, that's fine, Google data sets to supplement some of their other facilities like Google Images, Maps, Drive, and that's just to create searchable values for data sets. And large quantities already exist. Kaggle and Google.com is probably the first place that every data scientist looks for when they find a problem. You immediately will search for information and research and a place to start your investigation. And what often happens, especially in a commercialized web, when investors have an interest in getting their content to your eyeballs first, if they're selling you something, is that you get so many duplicates and so much unusable data that it can frustrate and flounder people and biological search engines like ourselves who are trying to construct models. Let me see. So in this, it's been the case for the last 20 years and continues to be in the future that finding the right data, the right values, the right research for your continued your continued problem is not a matter of looking for where it is, and you'll find it. It's for looking for what it is. If you consider the simple example of duplicate uploads of an educator and a student using the same data set, the same frame for different purposes, but in giving it separate titles, then the content is the same. The purposes were different, and they've each tagged their own interests when responsible for labeling the data themselves. This is in the case where the best practices in labeling and tagging are used, as is Google Dataset's new push with all their resources. But even in this best case scenario, this is only useful when the searcher has perfect knowledge. If a searcher has not already seen another data set, another lake, then they have no overlap. So to get a feel for the co-training model, let's see. Just imagine any simple learning algorithm that outputs "I don't know" on any example whose label it cannot deduce from the data. Very simple, so this is just one view. And n as a medium-sized number, something that would be feasible to observe, but unfeasible or expensive to label. I like to use an exponential distribution that x to 31 is reasonable, and then the way that it increases so rapidly climbs. So to avoid the "I don't know," the output in a single view is exactly the likelihood that the next element in our set has not been seen yet. That's an axiom of single view probabilities. So again, that's the probability that the next element in the set, m plus 1, has not been seen yet, and expressed from 1 to 0, from a surety that has not been seen to an attempt to reduce our error, the goal of any neural net. It does slope down, and it does approach 0, but we might need to go all the way up to the last element in the set just to cover a substantial fraction of an entire distribution. And in fact, an axiom of probability within one view is that the probability of this distribution of x1, that one view, multiplied by 1 minus its own probability, will cover the entire set, and that will describe the likelihood that the m plus 1 example has not been seen yet. So the formal framework for defining this co-training model, I would say, the important points are the bullet points, that each example is x1, x2, and those describe views of an example. I'm allowing D to be a distribution over X, and C being smaller concept classes defined on X. And the co-training model here, the fx that ends in L, is our definition of what allows for an existence of a label. If the function denotes the target concept over the entire field of L, then a view of one must be equal to the view of the second, which means that there's a label. If they overlap and they agree, then a label exists. And since this has a probability of greater than 0, this eliminates all the incompatible moments when the function of x1 and function of x2 do not agree. So those are assigned probability 0, and one way to look at that, that shows us how we can begin to reduce the noise and the unnecessary parts of our data, is to see this as a weighted graph. These are not as important, but here, these edges only exist if the example has this probability. And it is weighted technically because the way a neural net takes in data is to assign weights between all of the nodes and then continually adjust and re-update those hundreds of millions of times. And the edges that are solid are just ones that exist in a finite, feasible, countable n. So in theory, we would attempt to overlap these two conflicting, somewhat redundant, but independent views, just like the educator and the student would have overlapping but independent views on their data to produce this output space that is manageable by computer algorithms. And natural language is a broad topic, and human communication is inconsistent at the best of times, and really the nuts and bolts of the technology are only a small portion of the challenges that natural language processing faces. But still. So again, another definition of the compatible concepts would be those that have no cross edges. And even without knowing the labels, an algorithm can determine that when the edges terminate in the same endpoint, they must have the same classifier. So avoiding ones that end in the same endpoint would be the compatible concepts. So when this was carried out in practice, it was labeling computer science homepages by making a simple web scraper and finding them amongst all of the faculty web pages. There are a lot of potentially useful predictors. For example, this one was seeing the word handouts on a web page. And if it does appear on a significant number of these web pages, and there are some course homepages that don't include the word handouts, but more course homepages include the word than do not include, then that's sufficient evidence for this being an initial weak predictor. And that is where the true magic of machine learning is, that a weak predictor is enough for these concepts. And in this paper, 95% of these web pages were correctly identified, with only 12 labeled examples, compared to the manpower and human hours of labeling almost 800 web pages. We begin to see some of the benefits and possible futures of machine learning. Has anyone seen this sentence before? I first read it from Bill Bryson, who wrote The Mother Tongue and a lot of books that I was assigned to read in high school English. And I thought it was so clever that time flies like an arrow, fruit flies like a banana. But that's just an example of syntactic ambiguity, which means that even with perfect understanding of a dictionary, we get these garden path sentences in our linguistic syntax that is confusing to wrangle when we understand every word and we understand the noun, verb, adjective structure, and we still find incomprehensible patterns. So I tried to think of this not as postulating answers, because there are lots of punny examples that we can give to deflect current models, but as trying to postulate questions, as trying to approach and isolate issues so that once problems and questions are isolated, we can optimize around those. The common and legal patterns of vowel consonant patterns, that might be helpful, but it will not be sufficient. And the influence that hot day and hot dog should not mean the same thing in translation. So the conclusion of most of my research was that democratizing AI and machine learning, which is what was talked about if anyone attended the Women in Intelligent Machine Learning community panel, which was phenomenal, also relied on, of trying to find our questions and our issues and optimize around them instead of seeking a perfect situation. This co-training paper would not have been necessarily better if it had correctly categorized 99%, 99.8%. It may have overfitted a model. It may have absorbed too much of the training bias, and our own influences on what a correct test will always influence how our machines and our models are built. So there's a lot of future research. I saw some in challenging the premises and trying to make our own data more transparent and understand how our algorithms are deciding. But there are lots of future directions. Thank you so much, specifically to my faculty mentors, Chelio and Margaret Menzen, and to the Coding and Engineering Academy, and for everyone putting on this conference. that's it. Do you have any questions?
So for the actual question on categorizing which ones web pages are CS related or not, you basically inputted just the words or the HTML, like what was your input?
So I saw the views, like the X1 and X2, not as full documents, but as like attributes about them. And one attribute might be building, like, I remember building my first dictionary in Python and like using that to rank all of the words. So it could be a word sorting algorithm. One could be just ratio of, white space to dark text space. So any of them that would be attributes of that web document that could be redundant and could be overlapping, but the models do significantly worsen if they're more than 60% dependent. So if like one is counting handouts and the other one is counting assignments, like those would be too similar in the original research. And here's some of my code samples. Yeah. Any other questions? Yeah, in the back.
So you start with the small training set, and as you get more labels, you expand, right?
Yes, that's right, exactly.
Do we have so if you start with a little noise, like some bad labels are getting inserted, would that over time grow? You might be looking for pages that are CS, but you end up with pages that have some other characteristics.
Yes. Do you mean the problem of like falsely classifying and overconfident algorithms?
No, I mean because your previous decisions alter the training set. So you want to see a clean data set that everything that you have is correctly labeled. But as you get more false labels, at some point these false labels will overpower operations.
Yes, I see. So I would have a two-pronged approach and say that one of the benefits is that that an algorithm doesn't need to actually have labels. It can just find these edges in their endpoints and find that if they do terminate in the same place, then they must belong to the same classifier. And that's like only allowing perfect independence, and we lessened that, like I said, to about 50 to 60%. And you could bump that back up if you had enough examples, and you could train on hundreds of millions at a time, as opposed to that like tolerance in the risk profile that we accepted. And let me see, I would say that if I were to repeat this experiment or get grant funding, I would maybe consider building a recurrent net for that same issue, in that the patterns that you once saw should not be applied to every aspect of the data. It's looking for patterns as they occur, not just if you've done like image recognition with AI, it gets really good at detecting like a border, and then it can detect borders around every part of a photo, which you always want in photos, but that would hold you back if you're trying to look at video or sound data. So a recurrent net would learn differently, and that's what I would approach. Thank you.